Well, we're ready to start. Welcome back. We're about midway through week number 6. And the big announcement is we have our third exam that's on our way. I sent out this morning instructions for scheduling the third exam, but really just the same kind of instructions you've seen for the others. We pretty much have one more exam to get through, then the final exam will be on the table, and we're going to end on week 8. So already we're looking at the end of the summer semester when we're looking ahead to week number 7. Like we mentioned just last class, best way to get prepared for this exam, just like all the others, is to be fully caught up on all the homework sections. And this one is going up to section 4.7, the one that we finalized last class. Well, that's pretty much it for the announcements, other than we're on section 4.9. This will be the last section that we're covering in chapter 4. And really the role for what 4.9 plays in the bigger scheme of things is it's the connective glue that takes us from differentiation, chapters 3 and 4, into chapter 5, integration. We'll look into how that starts to go in section 5.1, probably today as well. But that's where we're at and where we're going. Any questions at all before we get started? Okay, well, let's jump in. Hopefully others make it in as well, but I appreciate you for making it in today. So 4.9, the title is mysterious. It says anti-derivatives, but really it's not too bad. It's going to be a good review on derivatives in its own right. Essentially, we're going backwards. And by backwards, we mean this definition specifically. We start with a function f. It's, in a lot of problems, going to be an unknown function, or excuse me, this will be the known function, and the antiderivative is going to be the unknown function. But to illustrate this definition, we'll go backwards just to see how it goes. So if f is continuous on some domain, D, then an uppercase function, f of x, is going to be called an antiderivative, just so long as if you differentiate uppercase f of x, you get the function in green, lowercase f of x. So as long as you differentiate this new function, you get the original one in green, you have an antiderivative. So that's the entire definition. It's kind of short and sweet. Just to illustrate how the definition goes, let's start off with just a made-up fast problem right here. We'll begin with the function f and say let f at x to be defined by something along the lines of, how about 7/3 x cubed plus 4x minus 1, just a random function. If that's our f of x function, then we can go ahead and differentiate it and see what the lowercase f of x function is going to be. So let's write out, this will imply f prime at x is equal to, when we differentiate this using properties of the derivative, we'll get 7x squared plus 4, and that's our function green. We could call this lowercase f of x if we like. So that's the whole illustration of the definition. Once we get this, we can now say this shows f is an antiderivative of lowercase f. Might as well hit that with the color coding just to keep everything consistent. So we have an antiderivative. In this problem, we had to discover what the f of x function is in lowercase. The actual questions we'll be doing in the examples and the homework. The lowercase f of x is known, and the idea is, what function uppercase f of x do you have to differentiate to get the known function? So the antiderivative becomes the unknown, and we're just going in this direction to once again illustrate the definition itself. It gets a little bit weirder. There's the idea of the most general antiderivative, and it has to do with some of our particular rules for taking a derivative. When we differentiate the constant -1, that went to 0, and we got the 7x squared minus 4. So that means we can play an interesting little game. Let Let's call this f sub 1, so a different uppercase function, x be equal to 7/3 x cubed plus 4x, let's say plus 5. It's not the same function. It differs by a constant. So this one is off by the 5 from the -1. But nonetheless, if you differentiate this, we'll get f prime at x equals, differentiate just like before, but we get the same exact function. This is now, let me bring back my colors. This now becomes 7x squared plus 4. It's equal to f of x again. So that's a bit weird, but it's the right derivative. And this tells us, this means f1 is also an antiderivative of lowercase f. So we found a new antiderivative. And now you can imagine this goes forever in a certain sense. You can just change whatever this constant is. There's infinitely many different real numbers you could put there as a constant. You could get fancy like pi to the power of e, any constant you want. Differentiate that constant, you get back to the lowercase f of x. And so there are truly infinite different antiderivatives of this lowercase function f that we see here. So antiderivatives have that weird feature. There are infinitely many different possible answers. Nonetheless, we can talk about the most general antiderivative. A lot of times we like to have an answer where we say the if possible. It really isn't going to be a unique answer, but what we do is we come up with an arbitrary constant c. What we mean by arbitrary constant is c is any real number. So if we allow that symbol to be any constant, any real number whatsoever, then we can write down just one answer. It's really an infinite family of different functions, but we can now say if f of x equals 7/3 x cubed plus 4x plus the arbitrary constant c, then f prime at x, same derivative, third time really, gives us 7x squared plus 4. The derivative of an arbitrary constant is still 0. Doesn't matter what symbol we put there. Differentiation with respect to x is 0. So we get this function. It's lowercase f of x. So we were able to differentiate some function f, get lowercase f of x once again, and if we can do that with an arbitrary constant, we'll call it the most general antiderivative of f. That takes a lot of oxygen to say, so instead we often abbreviate this with the understanding it's not one function, there's infinitely many different functions there. We still say this shows f is the antiderivative of lowercase f. So we use the definite article the, even though there's the understanding there's infinitely many different functions, but we're just abbreviating the most general antiderivative when we use the definite article the right there. So there is a unique answer to finding the most general antiderivative, lowercase f. This is the unique answer using the arbitrary constant of integration c. And that's the whole definition. Pretty much what we're going to practice with these notes is just working with these ideas of antiderivatives, seeing how it goes in this new landscape. But any questions with the initial definition? Okay, well, what we're going to need is some tools to help us with the next segment of problems. So let's add a bit to the notes here. We've got plenty of white space, so let's go ahead and add some more. before we get into example one, which is find the most general antiderivative of each of the following functions. And that could just be abbreviated to find the antiderivative, as the instructions in the homework will say. But before we begin taking a look at those problems, let's go back to the power rule. The power rule says if we differentiate with respect to x to the power of n, the process is the power n becomes a coefficient. The new power of x is one less, and that's what the power rule looked like. But now we want to unwind this, because this time we're not differentiating that function f there. What we're trying to come up with is the antiderivative. So this is like the function in green in the definition below. And the question is, what function do you have to differentiate to get the function in green? Once we find that function, we will have the most general antiderivative. So we need to take this power rule and figure out how to reverse it. That's going to be our first big formula in these notes. And this is the reversal. So power rule for antiderivatives goes like this. Let's follow our definition pretty much verbatim. We have a function f of x. Let's call it x to the power of n. We want the most general antiderivative. We'll call that an uppercase f of x. And here's the process. Because we are completely reversing the process of differentiation, we're essentially using this rule backwards, in every sense of the word backwards. Whatever was step one is the last step, in other words. Whatever was the last step here becomes the first step. The last step of the power rule was to decrease the exponent. That means it's the very first step, and we don't even decrease it. We go up by one. So we take x. As a first step, the exponent, it goes up by one. Now it's to the power of n plus one. And you can already see the danger here in a certain sense. Differentiation has a certain direction, exponent going down, but antiderivatives, or integration, we'll say later, the exponent goes up. So we have to track those in our minds and never get mixed up. So after the exponent goes up, we don't multiply by the new exponent. We reverse that as well. We divide by it. So we take 1 over n plus 1. It's multiplying x to the power of n plus 1. And we must throw in the arbitrary constant c. So that's our brand new rule, the power rule for antiderivatives. Just like the power rule is a major workhorse for differentiating, in the process of taking an antiderivative, this is possibly the most fundamental formula. The way we would check it is just differentiate this whole thing. If you take the derivative of this, n plus 1 comes down as a coefficient, but then you have n plus 1 divided by n plus 1. That's a cancellation. You take this exponent, n plus 1, it goes down by 1. That means it just becomes x to the power of n, and the derivative of the constant goes to 0. So if that's your f of x, the derivative of that is lowercase f of x. And so that means we have a true antiderivative, f of x. So with that idea, we can go term by term, finding the antiderivative of all these functions. It just requires a little bit of exponent surgery. That's not the most convenient exponent there. So let's rewrite f of x is 2x cubed minus x to the power 4.7 plus, if you take the cube root of x power 4, you get x to the power of 4/3 plus 12. So now, just keep in mind, this time we're not differentiating, we're taking the process and going in reverse. A lot of our rules work just as before. For example, in the antiderivative, there's a constant multiple rule. If you're finding the antiderivative of a constant multiplying, constant stays where it is. Then you move on to the next piece, find the antiderivative of x cubed. Well, if you have x cubed there, using the power rule in reverse for antiderivatives above, the new power becomes 4. It climbs up by 1. We divide by that new exponent. So 4 just goes under the 2. What we do next is we can move on to the next term, but it's a good idea, especially when you're doing these at first, is just pause for the moment. The property that this must have is f prime at x, the derivative of uppercase f of x, must be the original function, lowercase f of x. So if you find an antiderivative term, just mentally differentiate it right here and now. The derivative of 2/4 x power 4 would take the 4, it would come down, cancel with the 4 there. This would be 2 times x to the power of 1 less. That'd be power 3, and so it gives us the right term. So if you do a quick mental derivative term by term, or maybe get your whole answer and then differentiate the very last answer, then that's a good way to go. You're really just reinforcing how the derivative went as you discover what the antiderivative actually is. So that's 1 down, 3 more terms to go, but it's really just rinse and repeat. If there's a negative here, we just copy it down. I'm going to write down the base x after a little bit of space. The very first thing that happens is n plus 1. Here, the exponent n is 4.7, so add 1. Now it's a 5.7. We divide by that new exponent, so now it's 1 over 5.7. Or you could just say x divided by 5.7 if you want to simplify it that way. I'll leave those kind of stylistic choices always up to you. And then on to the next term. Go plus, add a little bit of space, add 1 to 4/3, that's adding 3 over 3 to get 7/3. We're dividing by 7/3, but we don't necessarily want to go like this, because now it's just taking a ton of vertical space, which is usually not space you want to waste, and it's also going to cause more steps simplifying it down. Instead, what we would typically always do is, once you have the new exponent, dividing by the fraction just means multiplied by the reciprocal, so we would write that in as a 3/7. Then pause. If you were to differentiate that, 7/3 comes up front as a coefficient and multiplies the reciprocal 3/7, so they just cancel out. We would subtract 3 over 3 here, but that would give you back to 4/3. So we're on the right track. The derivative of all of our terms so far gives us back all of the original terms for f of x so far. And we're almost done. If we were differentiating, we would say the derivative of a constant is 0. But we're finding an antiderivative, so it's a different process this time. If you have a constant, the antiderivative of a constant is always just tack on a variable. You get x, just tack that on and you're all set. It's kind of nice in a way. And what's the check? If you differentiate 12x, you just get 12 right back, the original term up here. So it follows the logic that we expect, taking the antiderivative. Then at this stage, it's still not done. This is something that we have to be aware of every time we take an antiderivative. We'll see some of the reasons why remembering that constant c is really important. In some kind of problems, differential equations, not including that c could mess up the whole entire problem. Also, when it says the most general antiderivative, it implies we must always go plus c. It's worth credit as well. If you forgot the constant on a homework problem and it's 5 points, it's worth 1 point. Just enough points to have a reminder, really, that it has to be there. So let's make a comment here on homework and exams. This constant, this is sometimes called a constant of integration. We might as well name it that now. This constant of integration must be here for full credit. And it's honestly easy to forget. So if you notice I forget one, let me know. We'll fix it right away. So that's our whole thing. it simplifies right here. So let's take our time to actually simplify it. F of x is 1/2 x power 4. I'll leave this as the fraction 1 over 5.7. X to the power 5.7 plus 3/7 x to the power 7/3 plus 12x plus the constant. That's a lot of work for just a tiny reduction there. That's always worth it. And that's our antiderivative of the original given function f. We did have to do some algebraic manipulation on the radical notation, just so we can use a power rule in the normal way. But aside from that, that's the name of the new game. So what we'll do is practice more of these kind of problems, take a brief look into differential equations, and then we'll be in chapter 5, and we're going to be looking into integration to end the day. But any questions with our first example down? Okay, let's try out the next. This one is similar as before. There's a mixture of power functions there as well as trig functions. Here's our power rule in reverse, just for easy reference as we're going. And just like in the last problem, probably the first thing we should do is try to clean this up algebraically as much as possible. So we can say this whole original function, let me just rename it, f of x, is better written for the purpose of using our power rule in reverse as this. I have really a 1/2 times x to the exponent, the power of 1/2. That's a little bit easier for our eyes to work if we're using this rule down below to separate things out. This one is just as bad. We can take this and write it as 2, bump x up to the numerator, and the new exponent would be negative 1/2. And nothing you can do with these trig functions. Well, not in this case, although you should always look if you can use some trigonometric identities to simplify. Well, let's just copy them in as cosecant squared x plus sine of x. So we need to find the antiderivative of all 4 of those terms. First 2 terms, we'll use the power rule in reverse. But the last 2 terms, we now have to dig deep back into chapter 3 for where our derivatives were for the trigonometric functions. So to start this out, just like with taking derivatives, for the antiderivatives, we can just go term by term by term. So let's start right here. For the constant multiple rule, we can just put the 1/2 in, then write in the base x where the red dot is. From the rule down below, in the antiderivative, we add 1 to 1/2. So that's adding 2 over 2 for a power 3/2. So that's the n plus 1 part right there. We divide by that new exponent. The new exponent is 3/2. So dividing by it is really multiplying by the reciprocal 2/3. And we can simplify those fractions on the next step. Then next term, same song and dance, just different exponent. Go plus 2. Put in a little space. We add 1 to this exponent for the antiderivative, so that's adding 2 over 2, giving us 1/2. This time when we multiply by the reciprocal, that's just a 2, so I'll go times 2 and put in more space than really needed. And those are the first 2 terms down. So recall the answer here when we differentiate uppercase f of x must give us back lowercase f of x, which is in this form. So here's where it's a good idea to pause and just double check. Mentally differentiate those. 3/2 comes down, cancels the 2/3. We would subtract 2 over 2 to get 1/2. And we're back to this function. If we differentiate the second term, 1/2 comes down. We'll cancel with this 2. Then it's going to be 2 times x to the power of 1 less when we take the derivative. That's minus 2 over 2 to get negative 1/2. So that's the right derivative there, 2x to the power negative 1/2. So now next, we need to handle cosecant squared of x and sine of x. So here's where, again, we go back to all of the work that we were looking in at chapter 3. Our formulas for, say, the trigonometric functions, or the inverse trigonometric functions, they're actually a set of two formulas. This is written as a formula for a derivative, but if we want an antiderivative, we just go from the right-hand side to the left-hand side. Let's throw this on the notes as the table, just as we see it, just to emphasize how we're going to work this table. Okay, that should give us enough space. So we have a cosecant squared x here. Let me highlight that in green. We want the antiderivative of cosecant squared x. So we have to ask ourselves, when did we ever differentiate something and got a positive cosecant squared x? This is close, right? Except it's negative cosecant squared x. It's slightly unfortunate, but you can fix that formula. Here's what you would do. The negative is in the wrong spot, just move it around. You can say, by the constant multiple rule, d by dx of negative cotangent x would then be cosecant squared x, now positive. So there's our cosecant squared x. And the antiderivative is the thing you have to differentiate to get the function cosecant squared x. So that means the antiderivative of cosecant squared x becomes negative cotangent x. Our check is, if you differentiate cotangent x, you get negative cosecant squared x. So we threw in an extra negative sign so that it'll cancel, and we get positive cosecant squared x altogether. So that's the idea. That's one extra term down, one last one to go. Before we go to sign, any questions about handling cosecant squared? Okay, at this point, now that we're doing antiderivatives to prepare for integration in chapter 5, it's a good idea to review pretty much the entirety of chapter 3. This becomes an idea of pattern recognition, and this is one of the reasons why this was an extremely critical table to memorize. And same for this table over here, section 3.6, the inverse derivatives, the derivatives of inverse trigonometric functions, rather. So we'll work with this table as well. Both of them are highly critical to memorize, not just for Calculus 1, but Calculus 2 and Calculus 3, and any subject that uses calculus as a prerequisite. So next one is sine x. And we almost have sine x there, but it's the same idea. The derivative of cosine gives us negative sine x. That's not what we want. We want positive sine x. So we just include an extra negative sign. Go negative cosine x. Then differentiate this term. Derivative of cosine by the table below is negative sine times a negative sign, giving you back positive sine as required. That means we've got the right antiderivative. We add the arbitrary constant of integration. Now it's the most general antiderivative. And this finally finishes off the problem. So when trig gets involved, we go back to this table here. And all we need to do is simplify it further. Again, it's a pretty small simplification. We can rewrite f of x as 1/3 x to the power 3/2 plus 4 x to the power 1/2 minus cotangent x minus cosine x plus a constant c. So if you differentiate this function in blue, we get the 1 in green, or this right here when we manipulate it algebraically just a bit. That means we have a bona fide antiderivative. So that's our part B, and looks like, I believe part C is not too different. We're gonna have to scroll down to see it, but any questions with any of these so far? Okay, well, here's our part C. This one's kind of mysterious because here's f of x. We need to come up with a function, uppercase f of x in blue, such that when we differentiate that function right here in blue, we get 1 plus tangent squared x. We do know the antiderivative of 1 would be an x. We could put an x down there, differentiate x and you get a 1. But then we're stuck because this is a weird question. When have you differentiated something and got a tangent squared out? Really weird question in a certain sense, right? Sure, we've differentiated a tangent and got a secant squared out. We've differentiated a cotangent and got a negative cosecant squared out. But I don't think we've differentiated a function and got a tangent squared alone out. So this one is more of a reminder that sometimes we require trigonometric identities. This came up in chapter 3 plenty of times as well when we were differentiating trigonometric functions. That's a major idea for this example here. Coming up with an antiderivative is more touchy than differentiating. If we had to differentiate that function, no harm done by having something weird. We would just use the chain rule. We always have a good answer for differentiating, but antiderivatives are way more different. It's kind of like multiplication. It's easy to do this, even though we're going to make the calculator do it. It's easy to imagine that if you had the free time, you had the scratch paper, you could absolutely take 869 times 743. Not too big of a deal. So that's what multiplication goes like, but integration is more like this. If you have 645, 667, what is the product of prime numbers that gives you that? That's a much, much harder question. That's going to take you more scratch paper to come up with all the prime numbers that results, all the prime factors that gives you 645, 667. So multiplication's kind of like differentiation. We have the process, we can work that out. It could be tedious, but we'll get it done. Factoring is like integration. Sometimes when you put large numbers down, like say even larger, this one, trying to factor this down to primes is kind of like trying to come up with the antiderivative or integration of 1 plus tangent squared x. So sometimes if we're not sure how to start this off, think in terms of identities. One identity, anytime you're in the land of trigonometry, is always write this one down or thinking about this one. Cosine squared x plus sine squared x equals 1. Now, if you divide this whole thing by cosine squared, you would get 1 plus sine squared over cosine squared is tangent squared. 1 divided by cosine squared is secant squared. And it gives us a good identity to work with right away. We can now say f of x can just be re-expressed as 1 plus tangent squared x, really just a secant squared x. And that function is a lot nicer to deal with, because if you look into the table above, if you take the derivative of tangent, you will get a secant squared. So the original problem was like a mystery. What is the antiderivative of that? Especially if you took the antiderivative of 1, got an x, and now you need an antiderivative of tangent squared. We're kind of stuck. But if your function has been rewritten as secant squared, all the secrets are revealed. Say f of x is tangent x. We want the most general antiderivative, so we must put in the constant of integration, c. And the derivative of tangent is secant squared. Derivative of a constant goes to 0. And that's the function you differentiate to get secant squared, which is algebraically the same as 1 plus tangent squared x. So this one's really tricky. We need an identity. Always watch out for these. These are good identities to have ready to go. But any questions on getting through the second one here? Okay, now that we're thinking about trigonometric functions, I think the next one is also going to involve them in some way, shape, or form. It just looks a lot more mysterious. Antiderivative of 1 over 2x squared plus 1 minus this complicated mess right here. We can't take the antiderivative, divide by the antiderivative. It doesn't work for differentiating either. The derivative of this is not the derivative of the numerator, divide by the derivative of the denominator. It's more complicated than that. You'd want to bring x squared plus 1 up into the numerator. give the power -1, and then use the chain rule if you're differentiating that. This one will require the chain rule as well. And when you're going backwards, finding the antiderivative, that gets convoluted as well. So we can't just unwind numerator and denominator taking antiderivatives. We need to think of what was the function that we differentiated ever that gave us that. That's a tricky question. And what makes it even trickier is the constants. There's a 1/2 there, there's a -30 there, and even their algebraic forms. So a good strategy for this one is thinking in terms of pattern recognition. How would this function really be written down? The 1/2 that's there is not the big problem. The big problem for us is the 1 over x squared plus 1. But the textbook actually wrote that differently in a curious way. It often writes this as 1 over 1 plus x squared, because this is pattern recognition. That's the best way to write it. And now the question has boiled down to, on the first term, what have we ever differentiated that gave us a 1 over 1 plus x squared? There actually was something. While we're thinking about that one, let's give the second term the same treatment. Copy down the constant to -30. -30 isn't the problem. What is the problem is the 1 minus x squared to the power -1/2. Textbook would often write that differently. It would put the exponent, it would make the exponent positive, which puts the base in the denominator to a power of 1/2, and it would probably just write that as a square root. That would be then the square root of 1 minus x squared in a denominator. So with that setup, we can now discover the antiderivative, uppercase f of x. But again, it's purely pattern recognition. We have to dig deep and think, when we were in chapter 3 and we were looking at all of our properties for derivatives, what did we ever differentiate to get 1 over 1 plus x squared or 1 over square root 1 minus x squared? And there was absolutely something. In the derivatives of logarithmic functions, it also contains the derivatives of the inverse trigonometric functions. These derivatives came up on exam 2. They're important enough for that. There were plenty of them in the homework as well. And when we first looked at them, this is kind of how we organized the chart with the color coding. It's a lot to keep in your head, but they grouped nicely. Sine inverse, cosine inverse just differs by a negative sign. Tangent inverse, cotangent inverse, same story. It's almost the same function. And same with cosecant inverse, secant inverse. So let's drop this on the notes for easy reference. This is now a table of 6 different differentiation formulas. That means there's 12 formulas there, really, because they also do double duty as antiderivatives formulas or integration formulas, we'll say pretty soon in chapter 5. So if you see a 1 over 1 plus x squared, here it is, miraculously. We can answer the question, what did we ever differentiate to get that? The answer was tangent inverse. The derivative of tangent inverse is 1 over 1 plus x squared. So finding this antiderivative, constant multiple rule allows us to carry in the 1/2 times. Now, antiderivative, and I didn't need that fraction. Let me control Z that out of there. There we go. Now next, the antiderivative of 1 over 1 plus x squared is the inverse tangent function. It becomes 1/2 tangent inverse at x. So that piece is completely done. Then go -30. And you have to recognize this algebraic form right here. This is tied in with sine inverse, the antiderivative of 1 over 1 plus x squared, 1 over the square root 1 minus x squared is the sine inverse function. So we just take sine inverse x, add the arbitrary constant c here, and the entire problem is complete right at that step. So notice how tricky some of these are. Watch out for these in the homework. These are also valid exam questions as well that could occur on the final exam, since this is now content not on exam 3 at this point. Exam 3 ends in section 4.7. So if you have a table like this ready to go, the thing you want to keep in mind is if this is on your page of notes for the final exam, Going left to right is differentiating, but going from the right to the left is coming up with the antiderivative. Well, that problem is done. The table really resolved it once we could recognize the components up here, separate out the constants, and focus on these structures to really see how the patterns match up. We have one more to get through. F of x is 1 over x. But any questions at the moment? Okay, even though part E looks like just a silly function, silly problem, it's actually the sneakiest, the trickiest problem on this entire example one that we're solving. If we were differentiating this, it's no big deal. You could just rewrite f of x is x power negative 1. Then that would imply that the derivative f prime at x is negative x power negative 2, or some people prefer to write it as negative 1 over x squared. And then our job is done. There's nothing further to that story, but that's not what we're doing. We are trying to unwind what is the function uppercase f of x that you must differentiate to get a 1 over x. And we've done that. We've seen that occur before. Let's first mention what some of the problems are with this. So let's take a quick breather. I want to scroll up and grab this once again. I lost my screenshot on that. So here's the fresh one. The power rule helped us deal with 2x cubed. It helped us deal with 2 over x power 1/2. So we just rewrote it, used the power rule. But there is one thing that's kind of strange and sneaky about this power rule. Let's put it down below as we think about it and discuss it. For that particular power rule, there is one thing you cannot use. You can never use this when n is negative 1. And you can see right away what the issue is. If n is negative 1, then right here, you have divided by 0. It's negative 1 plus 1. So even though we didn't make a big deal out of it, we probably should at this stage. This is for n not equal to negative 1. In other words, that means it fails as a formula for y equals 1 over x. Because when you bring that x back up to the numerator, the actual exponent n is negative 1, and you cannot add 1 to that, getting a 0, and then divide by 0 in the power rule. That's going to be an immediate breakdown. So this is really very, very weird. The more you study this, for every other power function, x power n, there is an automatic antiderivative, and your job is done. It looks like this. You just move around the powers in that kind of way. With one exception, if it's negative 1, the whole thing falls flat on its face. It breaks down 100%. That is extremely bizarre. Nonetheless, this problem is solvable. There is an antiderivative for 1 over x. We can find it. It's a little bit more weirder than you might expect. If you're thinking, well, it should be the natural log x because the derivative of natural log x is 1 over x, good on you, but there's actually a little bit more to that story. Natural log x, it just has a finite denominator, which is a problem, or excuse me, a restricted denominator. Not denominator, let me try again. Natural log x has a restricted domain. You can't put a negative number inside of a natural logarithm. For our most general antiderivative, we want our domain to be as big as possible. And so we're going to be using this here. Hang on, I think it's somewhere. I'm pretty sure I have it in my formulas. There it is. Finally, we're going to be using this here as our formula for the antiderivative. We know the derivative of natural log x is 1 over x, but the domain is restricted to non-negative real numbers. We put an absolute value of x on there. The derivative is still 1 over x. That's kind of miraculous in a certain sense. When x is positive, derivative of natural log x is the same as natural log x. But now the domain of this one includes negative numbers. It's defined for all non-zero x. And x can't be zero in the first place, so that's a great function to use. So we use this right here, and we say, anytime you see a 1 over x, the antiderivative is going to be the natural log of the absolute value of x, and then we have to throw in our arbitrary constant. This becomes essentially the next critical formula. After the power rule for antiderivatives, when you get to 1 over x, the one and only exception, this in its own right is a very important formula. So let's box it out. It just makes it feel important. Let's call it that, important formula. We'll use it in the chapter 5, and we'll get a good idea of its importance as well before very long in that chapter. And one thing to mention as well is that this part is also very, very important. For full credit, whenever we're taking an antiderivative of 1 over x, absolute values, is required for full credit. So these are formulas we're going to come back to. And in chapter 5, we'll see why the absolute value really is required by solving a particular problem that requires it. But for the moment, this is our rundown for antiderivatives. You'll be looking into very similar problems as well in the homework. And if you ever get stumped, don't hesitate to email and ask about it. But take a look into these tables, derivative of inverse trigonometric functions. That could be what unstucks the problem. Take a look into the derivative of trigonometric functions. And watch out for sneaky identities like these that might come up to get through the problem. So what we'll be looking into next is solving some basic differential equations, and then we'll turn it all over into chapter 5 to end the day. Well, any questions so far, getting through example 1? Okay, well, these are the main ideas of antiderivatives. The function that's known is the one in green. The antiderivative, uppercase in blue, is the unknown function that we have to determine whose derivative goes back to the given function. But now we're going to apply these into a couple interesting kind of problems. Here, we're looking into a basic differential equation. It's a differential equation because it involves a second derivative, and that means the function f of x is the unknown that we're trying to solve for. Down below is also a differential equation. It includes initial values, so sometimes this is called an initial value problem. In both cases, we're solving for the function f. Actually, let's change around the color coding there so we don't do a backflip in our mind. So we have a given function. This is like the one in green that we've been doing in the prior problems. Well, we want to undo, this time, two derivatives because there's a second derivative there, and come up with the function f, the function for which, if we differentiate it 2 times, we get this f double prime function here. But really all we're doing is taking a bunch of antiderivatives. If the second derivative of a function is 7x minus 1, we can come up with the first derivative of that function. Let's call it f prime at x. And from one step to the other, all we're doing is, let's put here on the notes, take the antiderivative. So notice we're only peeling off one derivative if that's the second derivative. If it was the fifth derivative, we'd go down to the fourth derivative and so on to match the pattern. But aside from that, we're doing the same exact things as we've done before. To find the antiderivative of the first function, 7x, copy 7, write in x. In green, it's to power 1. That means in the antiderivative, we go up to a new power 2. Divide by that new power. So 2 would go there. And that's our first term in the first level of the antiderivative. If you differentiate this mentally, 2 comes down, cancels with that 2, and you just get the original 7x. Then that was so fun, we just do it again. Antiderivative of a constant we mentioned before is just that constant times x. So you could write this in as -1 times x, but we would often just say negative x altogether. The derivative of negative x is -1. So we're on our way so far. But don't forget, when it says solve for the function f, really what we're finding is the most general antiderivative possible. There's no the function. There's an infinite family of functions. So we must put down an arbitrary constant of integration and go plus c. So that's one step down. Now we just do it all over again. We need the next antiderivative. So with f prime down, our answer, take off a prime, and we get the original function f of x. We're doing the same thing again. I'll just say briefly, antiderivative. And same process as before. We have a 7/2 here. I'll write it in as 7/2, but if you do the step mentally, no harm done. We're just trying to show the steps, so I'll take an extra step on this one. Take 7/2, move over before you write the base x, and the power just goes up again. It goes from power 2 to power 3, which means we need to divide by 3. We'll multiply by the reciprocal, 1/3, like we've done on the others. Same song and dance with this one, go negative. The power next, it goes up to power 2. Then divide by 2, so I'll go 1/2. So -1/2 times x squared. Differentiate this, and you would just get back to negative x as before. This one's weird, but it's no different than the -1. When we took the antiderivative of a constant, we just tacked on x. C is also a constant. It's just any real number whatsoever, any constant. So all you do for that constant is multiply it by x, and you have the antiderivative of that term. So if you differentiate c times x by the constant multiple rule, x vanishes, but c stays put. So you get the c back here. But every time you take an antiderivative, you get a new constant of integration. So there was an arbitrary constant here, but take another antiderivative and there's a new arbitrary constant. And we can't say c anymore. We need to add on a new letter. We'll just go down the line of the alphabet to add D to it. The reason C is not allowed is, if you put C here, it's implying that the constant here and the constant here by x had to be the same. These can be any constants. They don't have to be the same. They can be, but they're allowed to be different as well. So we have to put down a new letter to say the new arbitrary constant. So simplifying this further, not a whole lot to do. This becomes 7/6 x cubed minus 1/2 x squared plus cx plus d. And there are infinitely many different families or different functions here. When you select a value for c, even if it's 0, and select a value for d, you get one possibility for a function f, for which if you take the second derivative, you get back to 7x minus 1. So that's our application so far. We're going to do a closer application using acceleration, velocity, and position function, a closer application to something along the lines of, say, physics. But this is a good stepping stone before we look into that next application. Before we do that, we're going to see this initial value problem as well, see how this one goes. When Maddie says, are there any other steps, labeling we need to do on these questions to get full points? Not all. I would say that this is the minimum amount of steps you would have to put down for full credit, absolutely. In fact, you could have skipped a step from going from here to 7/2 x squared to this one, because what people tend to do mentally is they say, well, x is going to go up to power 3, then it would divide by 3, so that would just be 2/6 in the denominator, and just jump down to that. So that'd be a good shortcut to take as well. But as far as full credit goes, this would be absolutely for full credit. Any other questions or comments at the moment? Okay, thanks for asking about that one. And here's our next one. Again, it's a very similar problem. The one that we started with was a differential equation. That word has come up before in section 3.8 on exponential growth, exponential decay. This one's also a differential equation because the solution to that equation there is some unknown function f, but it has values. It has a value for the derivative. It has a value for the unknown function f. Because there's initial values, we'll often call these. This one is sometimes called an initial value problem, which is a shorthand for it's a differential equation, but two extra values as well that we want to specify, a value for the derivative, a value for the function. The thing about the initial value problems is sometimes when we're solving an application, we don't want infinitely many functions like we did in part A. Sometimes we have stipulations on what the function has to do. So what this is going to do, f prime at 0 is 1, is solve for the constant, say, c. It'll tell us exactly what it is. F at negative 1 equals 10 will solve for the constant d. So we're going to get exactly one and only one function, not an arbitrary family of functions like we did in part A. Aside from that, the calculus goes in the same kind of way. We peel off the primes, finding antiderivative after antiderivative, and then also use this information to solve for the unknown constants. So let's give this a try, see how it goes. On the first level, it's the second derivative, so we're going to call this just f prime at x. Now, we play this rule for now the power function in reverse for antiderivatives. I'll put in 3, put in a little bit of space. The new exponent on x is 3, which means we would multiply by 1/3. But if you were looking ahead and you knew it was going to be a power 3, and then 3 would cancel with the 1/3, again, that's a good shortcut to take on this one as well. Antiderivative of negative 1 would just be negative x. And so simplifying further, f prime at x is now x cubed minus x. You know, I did forget one thing. Don't forget to do this one thing. When you find an antiderivative, you need the constant of integration. I totally forgot it here, so let me put it in. Plus c plus c. So there's f prime at x. And now we have f prime at 0 equals 1. Here's f prime at any value of x written down here. So we can use the derivative we have, the initial value supplied, use that to determine what c is right away. If we forgot to put c down, then it would be mysterious what this is all about. Our end answer wouldn't be correct any longer. So that's one reason why that constant c must be included right when you take the antiderivative. Now let's use this information, the initial value, f prime at 0 equals 1. Well, we have f prime at any x. Throw in 0, and that would mean on the left-hand side, 0 cubed minus 0 plus the constant c is 1. And that's kind of a nicer equation. This just means right away, c equals 1. Sometimes the equation is a little bit more involved. We have to move things over, solve for the constant c. But this one automatically tells us c has to be 1, so we just plug it in. Now f prime at x is x cubed minus x plus 1. From there, we can go down to the next level, come up with the f of x function, and then use this initial value right here to solve for the new constant that we're going to get. So it's as if we're doing the same exact problem before, but now if it's an initial value problem, also solve for the constants as you go. So we're ready for the f of x function. For f of x, take the antiderivative as we've been doing. For the antiderivative of x cubed, first thing is increase the exponent to power 4, then divide by the exponent. Then do it again on this one. It's to power 1, so I'll go minus, a little bit of space. It's now to power 2, so I'll take 1/2 times x power 2. And you can format these differently, like I mentioned before. If you go like this, negative x squared over 2, same idea, just really a stylistic choice for writing it. Then finally, we have a constant 1. This will turn into just an x. Derivative of x is 1, so we're on the right track. The last thing is the constant of integration. You call it c here again. I would say no harm done, but c feels like it's already been used up once. It's already in scope of the whole problem. But I'd say the best practice is just to choose the next letter. Put in a constant d, and now we're going to solve for that different constant. We'll just use that initial value right there. We have f of x. We can use f at -1 is 10 to solve for d. Any questions to get to this stage, however, just getting that antiderivative? Okay, let's go back to that initial equation, or excuse me, initial value. F at -1 is 10. Well, just plug -1 on the left-hand side. This time it looks like it's a little bit more annoying to solve, but we'll survive it. This is 1/4. X to the -1 to power 4 is just 1, so just a 1/4 there. Minus 1/2 times -1 to power 2 is just 1, so just a minus 1/2. Then minus 1 plus d is 10. So we can make this be a 1/4 minus 2/4 minus 4/4 plus d is 10. And then this would be altogether, let's see, -1/4 minus 4/4 looks like a -5/4 plus d is 40/4. And so that means our constant d, when we add 5/4 to both sides, becomes 45/4. We're still not there. We're not at our end answer. This next step is critical, but it's not anything too fancy. We still have to say what is the answer to the question, substitute in the value for the constant. This is not for a lot of credit, but I need to know that you know the end answer, the function that solves this, is this one. Let's say here, therefore, f of x is 1/4 x power 4 minus 1/2 x squared plus x. And then here's where our hard work with the initial condition got us, plus 45/4. So there's that last substitution. Kind of annoying to copy down the whole equation, just dropping in the one number. But that is finally the bona fide answer. Do differentiate this function twice. You will get 3x squared minus 1. But on top of that, this is exactly one function that also has the derivative at 0 is 1, and the function output at -1 is 10 exactly. So there it is. This is solving another differential equation, the so-called initial value problem. We'll put it to good use for a more interesting looking application on the next one. Before we take a look into the last problem on these notes, any last questions or comments at all with these antiderivatives? Okay, well, here's the last problem for section 4.9. It's not the world's most involved application, but it's a decent physics application. And it goes back to something that we were looking at really on the very first day of the class when we had position functions, a velocity function. It also has an acceleration function. So we have an acceleration function given. A particle is moving with that particular acceleration. This could be something in, say, the Large Hadron Collider over at CERN, where they're colliding protons around a magnetic track, or it could be something else. It's got a lot of oscillations inside of it. Maybe we're tracking just some random wave. But either way, here's the particle that we're tracking. We know that the position at time pi seconds is exactly 4. And you know, it would have been nice to have some units on this. Now that I'm looking at this a little bit closer, I think the textbook probably does give units. Let's add a little bit units on to this after the fact, just to make the problem more interesting. Let's say 4 meters. So that's the position at time pi seconds. There's a velocity of 10. So this would be in units of meters per second. Let me try to make that look a little bit nicer. That'll do the job. And I don't know why I got underlined. Let me see if I can fix that. There we go. So there's just a small correction there so we know what the units are. Here's the acceleration. That would be meters per second squared, but I'll just leave it in that format there. It's cosine t plus sine t. So we want to find the position of the particle at time t. Really, it's the same kind of problem that we've been doing before. The position of the particle would be this. We want to find s of t. So we need to kind of organize how this all goes. We saw before in chapters 2 and chapter 3 that if you take s prime at t, the derivative of that would give you the velocity. So the derivative of position is velocity. So that's how velocity comes into play here. We have an initial value for velocity, initial value for position. If you differentiate velocity or take the second derivative of position, either way you think about it, say s double prime, a t would be equal to v prime at t, which is then equal to a at t. Here's where we have the acceleration function. So the derivative of velocity, the rate of change of velocity, is acceleration. That's also just the second derivative of the position function. So in a real sense, acceleration is a second derivative, truly. That means it follows, oh, that's too much zoom, sorry about that. It follows this kind of problem. Acceleration is much like the f double prime function way up here. We want to unwind and get back to the f function that we eventually landed on. That's going to be the position function. So this one was just a generic problem, but it really works the same way here. If we were given acceleration, 2 initial values, we can find position. And that's kind of impressive in a way. Knowing acceleration gives you the position of something. One way this can be involved in other physics situations is we know the acceleration due to gravity near the surface of the Earth is about negative 9.8 meters per second squared. So using that information, you could find out the position of a rock that was dropped. If you know its initial height, its initial velocity. Same as idea here. We know an initial position, we know an initial velocity. We're going to use all of that with a given acceleration to find out the position of whatever this particle happened to be. So this is a massively applicable type of problem to physics, with the one problem, this is only tracking in one dimension. So maybe just height, maybe just distance horizontally from a starting point, something like that. Well, before we tackle the problem, any questions about it or any of the background information? Okay, let's give this a try. I'm going to copy the acceleration function down just to show the flow of all the functions as we move through these. A of t is cosine t plus sine t If we know acceleration, we can come up with velocity. V at t, let's do as we did in the last problem. To get v at t, we're not differentiating any longer. We're taking antiderivative. Well, this time we need the antiderivative of a trig function. So we have to ask ourselves, what function did we ever differentiate to get cosine? Turns out that one's not too bad. If you put a sine t here down, the derivative of sine is absolutely cosine. And if you double check, just to be sure, that's a good idea. The more and more you look at this table, the more it's just going to kind of sink into your head. It's going to become almost muscle memory. We just need to practice. This is not a bad idea to put down some note cards, things like that. Or maybe just write down this table with the column here, the right-hand column blank, and just do this as a drill at the start of a homework set, anything like that before you study. Fill out what all these derivatives equal. Because like we mentioned before, it's not just a table of derivatives, it's also a table of antiderivatives. So if you want to find the antiderivative of cosine, we think of cosine being on the right. We ask ourselves, what do you differentiate to get cosine? And it absolutely is sine x, or t for this case. Then we do it all over again, but notice how tricky this is. If you go plus cosine t, the derivative of cosine t is negative sine t. We already saw this happen once already in the notes, so we have to make an adjustment here. We have to go minus cosine t. Let's go back to the table. The reason for negative cosine t is if you differentiate cosine, you get negative sine at t. So throw in an extra negative for double negation so that we can end up at positive sine t. Then throw in our constant of integration plus c, and we have infinitely many different velocity functions, but it's a start. We're going to find the one and only velocity that at time pi/2 seconds is 10 meters per second. So that's our first layer down. We need to solve for the constant c using that information above. Any questions before we solve for the constant? Okay, let's put this value down. Let me recopy the equation. Velocity at pi/2 is 10. We have the velocity at any time, so we're going to go sine at pi/2 for the left-hand side, minus cosine at pi/2, plus the constant is 10. So we did the function evaluation on the left-hand side. Now we have to evaluate our trig functions. Sine at pi/2 is 1, cosine at pi/2 is 0, plus the constant is 10. And the equation's about done. This means the constant is 9. So we take that information, we go back to the velocity function, substitute that in for the constant. Now we know that the velocity for our particle, not velocity as any possible function, but the one and only velocity function that satisfies our problem is sine t minus cosine t plus 9 in units of meters per second. We're not where we need to be. We found the velocity at any time, but we want the position of the particle at any time. But however, if you know velocity, you will know position. We just do this again, unwind to s at t. By unwind, the actual technical term that we're doing is, just like before, take the antiderivative. Which means we need to ask and answer the question of, what function do you differentiate here for s that gives you the velocity function above? Well, to get a positive sign, we did that once already. That has to be a negative cosine at t. And to get a negative cosine t, well, if you put in negative sine t, the derivative of sine is positive cosine. That means the derivative of negative sine t would be negative cosine t. So we now have negatives on the first two coefficients. Now it's a constant, but for constants, we just tack on the variable t. We have a new constant of integration d that we have to use, but this is really good progress. Once we come up with whatever the constant d is through this initial value right here, s at pi is 4, our work is done. So this is infinitely many different candidate functions for the right position function. We're looking for the needle in the haystack, the point on the number line, the right number for d that satisfies that information right here. But it's just the same thing we did for that initial value, b at pi over 2. Let's rewrite this below. S at pi is 4 means the position of the particle at pi seconds exactly is 4 meters. We know the function at any time, so the left-hand side of that equation is negative cosine pi minus sine pi plus 9 times pi plus d is 4. So there's the substitution. Cosine at pi is -1, so this is negative of -1 minus sine at pi is 0 plus 9 pi plus d is 4. Kind of an awkward equation, but we can solve it just like we've done before. D is going to be equal to, this is a +1, so we subtract 1 and get 3. Subtract also 9 pi. So that's the constant d. And now we can conclude just by substituting in for that constant, 3 minus 9 pi. And our conclusion is the particle is really moving exactly with all that given information and initial values. Then the position at any time is, it's here. At time t, it's at negative cosine t minus sine t plus 9t plus 3 minus 9 pi. So that's the exact one and only function that has the right stipulation for velocity, acceleration, position, and it happens to have that exact acceleration all at once. Then these problems can get really, really fancy, but I didn't want to take too much time looking into lots of interesting physics problems, although they're interesting in their own right. What we're really going to do with this information is now apply antiderivatives to the so-called area problem. We're going to now go into chapter 5, where the topic will now be about integration next. So that's where we are. This is the last problem for the section 4.9, antiderivatives. Any last questions or comments before we take a look into the next chapter? Okay, well, antiderivatives are one of those concepts where it's now massively important and critical to chapter 5, but we put it down for just 2 sections because what we're going to start off in chapter 5 is setting up a particular kind of problem. It's kind of like how we started the course. We started with differentiation. But what is a derivative? It's the slope of a tangent line. And that means we had to start with what is a tangent line? How do you come up with the slopes of the tangent line? So we digress into limits for a little while. That's about what we're doing in chapter 5. So here's what the setup of the problem is going to look like that sets the stage for integration. Integration is all about finding areas. And here's the so-called area problem that's critical to the sciences that we find a good and efficient solution to. So we want to find the area of some region S. It's a bounded region, so the area to this is finite. It's the region that's under the curve of the function y equals f of x. It goes from A to B, so we put vertical lines there to bound it that way. And it's also, let's see, it's bounded by the horizontal axis. Does it say that anywhere? Lies under the curve from A to B. Let's also just add here, just for our own understanding, and above the x-axis. Just to be definite, I mean, it kind of indicates that there by the region. So we have really four different things bounding. The x-axis, vertical line segments, where the function starts at A, ends at B, and the function itself is the upper bound here, this way. So there's a definite area, and we want to find it. We're going to do this methodically in section 5.1. We're going to look into different rules for finding areas. Some of these rules get revisited again in a Calculus 2 setting, and they're useful in their own right. But the next topic that we really want to get into, after we define the integral in section 5.2, is the fundamental theorem of calculus, section 5.3. And I think this is just the right picture to say what that is, just so we know what is the value of antiderivatives in the first place, because we worked hard in section 4.9. We're going to come back to it, but let's give a preview to how we're going to solve this area problem when we actually use the fundamental theorem of calculus. So here is us using by the fundamental theorem of calculus. There's two parts. So this is part 2, sometimes called the evaluation theorem. We evaluate and get an area. The area right here is going to be dead on exact to, not an approximation, exactly equal to f at b minus f at a, where the a and b came from these values here that are bounding the area, where f is any, and we really mean any. The simplest one with the constant of integration set to 0 could be used, for example, is any antiderivative of f, lowercase f, the one that is the upper bound to this original curve. Same exact color coding as what we used in section 4.9, and that is a really bizarre statement here. I think it's one of those statements where if you have any doubt here, I don't blame you. It is a humongous connection. And this is what put Isaac Newton, Leibniz on the map for discoverers of calculus. They were the ones that independently came up with this radical connection. The textbook says this is one of the greater achievements of human intellect. What it's saying is somehow the process of antiderivatives is connected to the process of finding an area. And all the derivative was the slope of a tangent line. In one way, shape, or form, those are strongly connected processes. And again, the thing that's really weird about this is this curve can be very complicated. But if it's continuous, then it will have an antiderivative. And all that really matters is the antiderivative at the upper bound minus the antiderivative of the lower bound. Anything in the middle, no matter how crazy it got as a function, doesn't matter. The antiderivative gives you the dead-on exact area every single time. So that's the fundamental theorem of calculus part 3. To work our way towards it, we're going to first study this area problem from scratch and ask ourselves the question, how would you even approximate that area? So that's what we're going to take a look into next. But before we got into that, again, it's a good idea to show the connection for antiderivatives into solving this new problem. We'll say the process of finding this area will be called integration. Well, any questions about this process before we start approximating? Okay, let's take a look into the next example, see how this one goes. It's another application, but it's a decent one to take a look into. If you're talking about areas, probably the first thing you want to resolve is, what is the use of an area? We never said what a derivative is good for. The slope of a tangent line is useful in. then doing derivatives would feel kind of shallow and not super fulfilling. So this one kind of answers right away. One thing an area is good for, it can help us find a distance. But really any physical quantity, distance, energy, time, you could phrase it as an area problem. So this is more of a broad of an application that you might originally imagine. Finding areas is fundamental to the sciences and computations. So here's the landscape of this one. We have that the velocity graph of a car accelerating from rest to a speed of 120 kilometers per hour over a period of 30 seconds is shown. So imagine this is like the speedometer, but we also know the direction. The car is moving in a positive direction, so velocities are always positive. Here's the velocity, goes up to 120 kilometers per hour over a period of 0 to 30 seconds. So that's kind of nice to know in a way. But what we really want to find out is if we can track that velocity, we should know how far it went, right? We should know the distance of the car. That's what we actually want to calculate, distance. We're going to do this by using 6 approximate rectangles at right endpoints. So that's how we're going to approximate that distance. It turns out the distance is just the area under this curve, and that's probably a weird thought. But we're going to investigate this really closely. This is our premier example for why we care about areas and integration. So maybe the first thought we would have is in, say, an algebra class or a physics class, distance is equal to a rate times time. So that's all distance really is, how fast you're going, how long you went. Usually that's an average rate of speed, and our rate is kind of awkward. It goes slow and it's accelerating, it's speeding up. So I don't want to use, say, the rate of 120 kilometers. That'd be using a rectangle that goes like this, a time of 30 seconds. If we took a rate 120 times a time of 30 seconds, we're finding the area of that rectangle, but that's a humongous overestimate of distance, right? Similarly, we wouldn't want to use a rate of, say, maybe 50 kilometers per hour over a period of 30 seconds. It would look like this. That rectangle is going to underestimate the distance by a long ways as well, because it wasn't just moving 50 kilometers per hour, it was going rather fast after a little short while. So we need to find a way to make a compromise. We want to make an estimate of what was the velocity at certain time intervals, and it tells us just how many to use. Use 6 approximate rectangles at right endpoints. So let's start off with that information. The number of approximate rectangles we'll often write as n. N equals 6 rectangles, not just one, like we indicated in those 2 extreme cases. For using 6 rectangles, we should say what are the points that they're going to be subdividing the interval from 0 to 30 seconds to. The leftmost point we'd often call A, or we could call X naught, which is 0 seconds. The car's at rest doing 0 kilometers per hour. Then of the next value, here's X1, 5 seconds. X2, likewise, is at 10 seconds. X3 is at 15 seconds. X4 at 20. X5 at 25. X6 at 30 seconds. So those are going to be the actual values. We're partitioning 0 to 30 in order to get rectangles out. Velocity is not going to be constant from 0 to 5 seconds, but if we use an estimated value somewhere in there, at least we're not going to be estimating as bluntly as we did before. This says to do this at right endpoints. What they mean by that is these in particular are the right endpoints. Let's start by just sketching the area. You'll be asked to do so as well in the homework exercises. Let's do it using this color. Now let me actually complete this axis. Here's 5, 15, 25. This is 20, 40, 60, 80, 100, and then it said it went to 120. So the first approximate rectangle that says to use right endpoints, then that's telling us what the height of the rectangle is. From 0 to 5, the right endpoint would be at this height here. We're going to estimate from the interval of time, 0 to 5 seconds, it was doing about whatever the height of that rectangle is, about, say, 50 kilometers per hour. So if we find this area, we have a rate, we're estimating at 50 kilometers per hour. We have a time, 5 seconds, we'll multiply it. Will give us an approximated distance in the first 5 seconds. It's an overestimate, but it's not as severe as the very first rectangle we put down, estimating at 120 kilometers per hour. Then we go to the next point, 10. At 10, on the graph, we go up, hit the rectangle, go to the left. Looks like that's pretty close to 80 kilometers per hour. And that estimate is not as extreme. This area is a distance. It's a rate, 80 kilometers per hour times a time. Here to here, still 5 seconds. On every one will be 5 seconds. And that's the overestimate of distance. Not as bad. And it gets less bad as the curve flattens out. At the next one, 15 seconds, the right endpoint is here. That one is maybe something like 95 kilometers per hour is what we'll estimate for 5 seconds. Do it again at 20. Here's this one. At 20 seconds, it's getting harder to estimate these. I would probably guess maybe 110 kilometers per hour. 25 seconds, it's getting to its maximum velocity, maybe 118 kilometers per hour. And then at 30 seconds, that's when it reaches the top speed in this interval, 120 kilometers per hour. So if we just estimate over this entire interval, 25 to 30 seconds, the driver did 120 kilometers per hour, we can take the rate, 120 kilometers per hour, times the length of time, 5 seconds, and get an approximated distance from this time frame as well. It's going to be an overestimate because we see the overage in area every step of the way, but these estimates only get better and better and better as you use more approximate rectangles, say 60 instead of 6. That's just kind of nasty work to do as a human. That's a lot of writing things down. So that's the picture so far. That's approximating rectangles. Let's put down something else. We have the rates. That's going this way for rates. The time is 5 seconds each time, but there's a particular formula for that. We'll either call it delta x, or in this case, a delta t. It's always going to be b minus a divided by n. We have the a value here. I forgot to indicate down below. B value is also x6, the largest number. So we're just taking an b value, 30 seconds, minus an a value, 0 seconds, divide by 6, and we get 5. So delta t is 5 seconds. Notice the unfortunate thing, this is in kilometers per hour, so we do need a unit conversion. Let's do the unit conversion at the very end so we can focus on the fundamental ideas first. So now, putting this all together, we can say distance is going to be approximately equal to, we're using 6 approximate rectangles at right endpoints, and we'll shorthand that to R6. Here means right endpoints, so R. 6 is the approximate rectangles, 6 of them. It's going to be delta t times velocity at time 1 plus velocity at time 2 plus velocity at time 3 plus velocity at time 4 plus velocity at time 5, and I really thought that was going to fit. Let's drop a line, plus velocity at time 6. And you know what? I should have called those times instead of x's. Let's fix that and call it t for time. just for the sake of total consistency here. Sorry for backtracking that, especially if you're writing in pen today. I must like the variable x. It just seems to crop in often. Let's make sure they're all t for times. So that's our formula. That means the distance will be approximately equal to, well, all this comes out as we plug in the value for delta t, 5 seconds, we're going to need a unit change. We're going to grab values for the graph, drop them inside here, and we could probably do that in 5 minutes, but I think that's kind of racing through it. So on the next steps, sorry, I thought we were going to be able to finish this one before we got to the end minutes. I guess it took a while to draw everything out. But on the final steps, when we come back to this problem tomorrow's class on Wednesday, we'll plug in the value for delta t, the 5 seconds. We'll plug in the value for all the velocities, all those particular times that are given, and we'll crank out to that approximated distance. So that's a process of finding areas. We're going to take another look at it, find the area under the graph of, say, cosine, area under the graph of 1 over 1 plus x squared, sometimes using midpoints, sometimes using left endpoints, and example 1, we're using right endpoints. So we'll see how these estimate changes as we make different decisions. What should be the height of the rectangle across the interval? This is the picture for right endpoints, and it changes for left endpoints and midpoints, and there's a whole bunch of other rules for these kind of approximations. But again, sorry for breaking this problem in half. We'll do the evaluation, finalize it, and move forward on Wednesday's class. But any last questions or comments at all, folks, before we call it a day? Okay, well, this will be our stopping point for today. And by the way, they were able to fix the problem with the classroom 216 being locked down for a different event. I'll be in room 219. I made an announcement about it till the end of the semester, provided nothing else weird happens. So I'll keep you posted if anything weird happens with the classroom. But have a great night, folks. We'll come back to this and work through section 5.2 on our next class. Take care.